Hello, my name is Oyvind, and my project thesis is an investigation of the turbine governing. But before I get to the governor, I want to say a few words about the domain in which the governor operates, which is the asynchronous power generation unit. So I made a small figure, and I'm sorry about the language for your English speakers, but the governor is this block right here, which senses the RPMs of this power unit and calculates the openings of the guide vanes of the turbine based on the PID algorithm. So the objective of the unit is to convert the inertial power to electrical active power, and this is done on the Nordic synchronous grid, the power grid, which means that this unit must be synchronous with the RPMs or the frequency of the grid. So the grid looks kind of like this. It's parted in regions, which are these red lines, and the blue lines you can see the power flow, which was, I think this was just a week ago. And these are all synchronous. You want to have the same frequency. It can be looked on as a wheel, as a really heavy wheel with a lot of inertia, which all the power units, which are synchronous, are directly connected to this wheel, and the consumer extracts the inertial power, and the power units deliver it to the grid. And the governor is a really important device which controls the power in the grid. But if a connection fails, or if there's supposed to be work on the grid, you have to maybe disconnect an entire region or a smaller region which can have one or more power plants, which means you can have to go to Iceland mode. And it's not, of course, not the island Iceland, but it's a good analogy because here you have an isolated system. And the trouble now is for the governor, because now it has to govern both the frequency and the power. It becomes a much less inertial system. It has more instability. So the governor algorithm looks like this. It's not as complicated as it looks. So if you remember the figure from earlier slides, then N would be the RPMs of the power units, and the reference is just 50 Hertz, or the rotation based on the number of pole pairs on the generator, and you find the reference. And this is what you want. This is the value that you want the governor to track, which is we call this an E, error, or a deviation. And we input this into this is the standard PID algorithm, but in many cases it's different. This is just the educational version that's easiest to explain how it looks. So based on these three terms, it calculates the output, which is fed into the servo, which is like a hydraulic piston, which amplifies the signal and moves the guide vanes to open and close the turbine flow rates to govern the power and the frequency. So in this governor needs to be tuned properly. If it's tuned wrong, it can become unstable and cause dangerous transients in the system. And what you do is you first tune so K is the proportional gain. If you take away all these terms, you're left with a proportional governor, which is just, the output is just directly proportional to the deviation of the frequency. So this cannot eliminate the steady state error, but it can also be a very powerful tool. If you want to eliminate the steady state error, you can also integrate the error and have this time constant, which, yeah, I don't have time to go into it. But the differential term is the last one, which determines how fast it acts. It looks at the gradient of the deviation and kind of predicts the future if you want. And then you set the droop, which is a way to distribute the power between the synchronous generators on the grid. Because if you didn't have this, you wouldn't know how the power was distributed, and it could cause dangerous transients. And what it does, it makes a small error if the power drops, or so if the consumers are extracting too much power from the system, the frequency will drop. And if the governors didn't have droop, then they would stabilize the frequency, but it would stabilize at the final value, which is already dropped. So you want the frequency to go back up, and you want all the generators to cooperate. That's why you create this steady state error or not steady state, but it's an error, so that all the synchronous generators cooperate together to get all the, because it's a very heavy system, so you need everyone to cooperate at the same time. So I've probably already said this. There are many methods for tuning the governor. Some are analytical, some are automatical, but the mostly used are experimental, and which is just the simplest also. They all gravitate around finding the optimal 3 PID parameters, hence the name. And every dynamic system has their own unique behavior, so you can't just find one set and apply for all. You have to tune every system. I'm getting to my thesis objective, but this is part of it. So there are some changes in the grid functional requirements, which is partly due to an increase in low in energy sources, which are low in secondary reserves, which means like solar and wind, especially a lot in Europe. We are getting more connected. They have a small, they don't have the potential like water power has to. If the frequency drops, you have a big reservoir, you can just flood all the water into the system and just to boost this frequency back up. I forgot to say something about the changes. Wait. There's a missing slide there, but the changes, oh, there's it. So this is the droop. It looks like this, the red line from right now. All the generators must have a droop like this, and they now want to introduce a dead band in the middle frequency, so that when the frequency is good enough, you don't participate in the frequency governing. Also, you want to introduce the rate of change of frequency, which is kind of a measurement of how unstable the system is. If it drops, if this frequency drops below this red line, it must go into Iceland mode, because then it's not the stable system as the grid is anymore. Which means that then it can go over to a set of more stable PID parameters, which it is predetermined in the governor. So I'm simulating this in a software called LV-Trans, which is made by my professor Bjørnar Svingen in LabVIEW. It looks like this, and you can add together the elements which are programmed based on the pre-mentioned method of characteristics. It's a one-dimensional tool, and it's full transient simulations of the hydropower plant. I mainly look at the governor, and I look at different tunings, and I create. Okay, so I'm looking at how aggressively can you tune the governor before it becomes unstable on both grid and Iceland mode. Yeah. So how I do this, I generate Bode plots and Nyquist plots. Basically, it's how do you know if the system is stable or not. You can look at the margins. So if you look at the crossing frequency of 0 decibels, what is the phase margin at this point? Because if the phase margin is it's like how far away from 180 degrees, that's what you want to avoid. This has a very large phase margin, but you also have to look at the amplitude margin, which is when it crosses the 180 decibel, when it becomes opposite and oscillating, you don't want to have a too small gain. Also, you can look at, this is the same thing actually, you can look at this point, which is the imaginary frequency in the transfer function. When the open loop transfer function becomes -1, it blows up to infinity and it starts oscillating and amplifying, and then boom, it goes all the way. Thank you.